Hi, I'm Puneet Mehrotra, and with me here today is Vastavanand. We're from the Systopia group at UBC, and we're here to talk about a work on the Smooth Kronecker Graph Generator. This work was done by Daniel Margot as part of his PhD dissertation at Harvard University, where he was advised by Professor Marco Seltzer. The reason we're all gathered here today is because graphs are everywhere. A lot of data is naturally graph structured. For example, protein interaction networks, roadway networks, and social media interactions can all be represented as graphs. And to address this preponderance of graph structured data, there has been a lot of research in creating graph processing systems that are able to scale well and process ever larger data sets. In order to benchmark and test the scalability of these graph processing systems, researchers require massive data sets. There is, however, a dearth of large publicly available data sets. Of the not so large data sets that are available, a few get used most widely. One such example of a data set is the US Patent Citation Network's, the CIT patent dataset. It has around 3.7 million vertices and 16.5 million edges, and in its uncompressed format is 289 megabytes, which is small enough to fit in the memory on an iPhone 4. On the other hand of the spectrum is the Twitter crawl dataset from 2010. It has 41 million vertices and 1.4 billion edges, and in its uncompressed format is around 26 gigabytes. This is fairly big, but to put things in perspective, it is still small enough that it fits in the memory on our advisor's laptop. We measured this. To address this lack of publicly available datasets, researchers often turn towards synthetic graph generators. RMAT and Kronecker graph generators are the most widely used examples of this. In the RMAT and Kronecker graph generators, edges in the graph are generated in accordance to a 2x2 seed distribution, where each element in the distribution approximately corresponds to the fraction of edges in a particular quadrant of the final adjacency matrix of the graph. The generator produces a graph of some specific sizes on demand. The reason for the RMAT and Kronecker graph generator's popularity is that they're highly parallelizable, and it is easy to produce generative parameters that can be used to reproduce a test dataset. Furthermore, when the distribution is derived from that of a real graph, as the authors of RMAT and Kronecker intended and demonstrated, researchers can claim that the synthetic graph distributions are like that of a real graph and therefore represent valid experimental data. But Kronecker graphs are far from ideal. The degree distribution of a Kronecker graph is combed at regular intervals, between which the vertices with a given degree are highly improbable. This distribution matches no real-world dataset of which we are aware. This may affect algorithms such as triangle counting, whose expected runtime depends on the degree distribution. This combing is also present in the k-core distribution of a Kronecker graph. Moreover, as the scale factor, which controls the number of vertices of a Kronecker graph, increases, the proportion of isolated zero-degree vertices also increase. So if you create a Kronecker graph of scale factor 30, you would expect around a billion non-isolated vertices, but in reality, that number is somewhere closer to 400 million instead. So here we look at the degree distribution of some real-world graphs and compare that to that of a Kronecker graph. As you can see, the degree distribution from Twitter, CID patents, and the Salk Live Journal dataset are fairly smooth. And if you compare that to the degree distribution from a Kronecker graph, you can clearly see that the combing pattern is very visible and is unlike that present and is not present in any of the real-world graphs we compare to. The takeaway is that real graphs do not have comb degree distributions. And this degree distribution is not simply an artifact of the implementation of the Kronecker graph generator. We have found this combing in graphs generated from many widely used Kronecker graph generators. We show here the graph generated from Graph 500, Snap's Kronecker graph generator, and the Trillion G generator. You can see the combing pattern in all of them. One way to fix this combing is the addition of random noise, as was proposed by Seshadri. With the application of random noise, there are just as many expected degrees as there are vertices, and the degree distribution is less clustered. There is, however, no clear consensus on how much noise to add. Adding too much noise makes the graph incredibly easy to partition. So if you look at this graph here, if you add a lot of noise, you get the line which indicates the lowest communication cost, and a low communication cost implies a very highly partitionable graph. After adding the noise, if the off diagonal in the seed matrix becomes 0, then the graph becomes highly partitionable, which is not the case with what happens in a real graph. The important thing to note here is that the Seshadri's recommendation of noise addition was per graph and not per edge. So if you generate a real noise, you need to run the benchmark multiple times to test its convergence. But this results in benchmark comparability and cost issues because it is not immediately clear how many runs are needed to converge. Many people or implementations will just run it once, which exaggerates the problems that we've mentioned, especially if the noise plants a partition in the graph. Therefore, when we use the Kronecker graphs for benchmarking, it becomes essential to control for these random variables by running the benchmarks on a large number of such graphs. These problems call into question whether Kronecker graphs ought to be treated as representative datasets for benchmarking purposes. The reason for both these problems is that while Kronecker models a reasonable degree distribution, it is undersampled. This happens because each vertex's degree is determined by a non-unique sum of its binary representation. With the addition of noise, the vertex degrees still vary around undersampled model rather than the correct underlying model. Our solution is a smooth Kronecker graph generator, which resamples a different distribution from the underlying model and mixes it with the original 2x2 seed to smoothen the effect of the undersampling.
Before we discuss the Smooth Kronecker algorithm, let me give you a bit of a background about how the Kronecker product works. Kronecker product is a product between two matrices where each element in a matrix is multiplied with the whole other matrix. So, the Kronecker product of two 2x2 matrices will be a 4x4 matrix. The animated GIF on the right shows the Kronecker product of a 2x2 color matrix with itself up to 6 levels. Notice that the RGB value of black only contains 0, and with every Kronecker product, the zeros propagate across the whole matrix. Let us take a look at Kronecker multiplication in one dimension. We start with a 1x2 seed and obtain the Kronecker product with itself twice. Notice that after the first multiplication, we have 4 matrix elements, but only 3 unique values. As we continue multiplying, it only gets worse. The number of elements grows exponentially, while the number of unique values grows linearly. This is the reason as to why the original Kronecker model remains undersampled. Let us take a look as to how we can resample this 1x2 seed as a 1x3 seed. To resample this 1x2 seed with the elements A and B as a 1x3 seed with the elements X, Y, and Z, we sample the leftmost third, the middle third, and the rightmost third as the Kronecker product reaches infinity. For the leftmost third, the value is the geometric series with the initial term AA and ratio AB. For the rightmost third, the value is the geometric series with initial term BB and ratio AB. The value of middle third is simply calculated as 1 minus X minus Z, since the probabilities of the seed must sum up to 1. We are not resampling from the second level, but sampling from the infinite Kronecker product series. The second level Kronecker product is just shown here for illustration. Now, we need to resample a 2x2 seed as a 3x3 seed. We can do the same kind of resampling in higher dimensions like we did in the one dimension case. Each element of the 3x3 seed is sampled as the Kronecker product of the 2x2 seed as it goes to infinity. For example, the first element is sampled as the leftmost corner goes to infinity. Figure on the right shows the sampling of the first element. The sample consists of the whole of AA, the leftmost third of AB, the topmost third of AC, and the top left ninth of AD. Let's take a look at the Smooth Kronecker algorithm. Given an input of a 2x2 seed, the total number of required edges, scale factor 2 and scale factor 3, the algorithm first resamples the 2x2 seed as a 3x3 seed. The scale factor 2 and scale factor 3 collectively decide the total number of vertices in the graph. An edge is generated using scale factor 2 to scale factor 3 Kronecker iterations. Next, for each edge, the algorithm randomly determines which seed will be used for sampling at every Kronecker iteration. For example, for scale factor 2 equals 4 and scale factor 3 equals 2, a possible order is shown on the right. Note that the random order of the 2x2 and 3x3 seeds is rolled for each edge and not for the whole graph. So we don't need to run a scalability benchmark multiple times to reach convergence as we have to for the noisy Kronecker graphs. At every Kronecker iteration, we sample an element from the seed for this particular iteration. Based on the chosen element, we update the source and destination vertices of the edge. Let's take a look at the concrete example. For a graph with two 2x2 seeds and one 3x3 seed, the total number of possible vertices in the graph is 12. Thus, you can see a 12x12 adjacency matrix of the graph on the screen. Let us take a look at how an edge will be generated in this adjacency matrix. Here, before the Kronecker iterations for the edge, the source and the destination of the edge are initialized to be the vertex 0. In this first iteration, we sample the bottom right quadrant from the 2x2 seed and move the source and destination of the wedge to vertex 1 and 1 respectively. In the second iteration, we sample the middle element from the 3x3 seed and update the source and destination of the vertex. Finally, in the third iteration, we sample the bottom left quadrant from the 2x2 seed and obtain the final location of the source and destination of the generated edge. Steps 2 and 3 in the Kronecker algorithm are repeated until the desired number of edges are generated. Graphs generated using Smooth Kronecker have a smooth degree distribution, just like real graphs. I'm showing you degree distribution of 4 graphs, 3 of which are real graphs, and the other is a synthetic graph generated using Smooth Kronecker. Can you spot the synthetic graph? If you were able to spot the Smooth Kronecker graph correctly, congratulations, you have a keen eye for detail. The number of vertices in a Kronecker graph have been limited to powers of 2. With Smooth Kronecker, this is not the case, as Smooth Kronecker supports number of vertices that are a mix of powers of 2 and 3. To achieve the smoothing of the degree distribution, we only need to have one 3x3 resampled seed as shown in the figure. This is enough to counter the undersampling of the original Kronecker model. Note that Smooth Kronecker doesn't solve the 0-degree vertex problem. However, it does give you a way to deal with it. If you want n vertices, you look at the graph we showed earlier and figure out how many total vertices you need to target. Then you come up with a prime factorization that produces roughly that total and produces the right number of seeds required to obtain n number of vertices. So to summarize, Smooth Kronecker fixes the combing problem in the degree distributions of Kronecker graphs. It generates graphs better suited for running scalability benchmarks like triangle counting. Here, the graph generated using Smooth Kronecker has the highest runtime for 2 different algorithms of triangle counting on Galois, a popular graph processing system, as compared to the graphs generated using the original and noisy Kronecker models. Moreover, Smooth Kronecker provides these benefits without affecting the partitionability of the graph that is generated. Smooth Kronecker preserves the partitionability of the original Kronecker model, unlike the noisy Kronecker generators. In conclusion, we would like to urge the community to adopt the Smooth Kronecker for generating synthetic graphs for scalability experiments. The Smooth Kronecker generator is open source and publicly available for use on GitHub. Thank you.